a moment. This was completely okay. So let me hide the controls and there's quite a lot of noise. I don't know if it's the microphone. Okay. Oh, so I'll start. So again, thank you, Anton. Some work which was in collaboration with Sergei Petkov and Pavel Novichkov, which I collected under this title, Hierarchies, which I refer to fermion mass hierarchies from residual modular symmetries and modulus stabilisation. So don't get scared with this huge title. I will try to be to outline first what I will do. I'll talk about what modular symmetries are, why do we want them, how they work, and then I'll tell you about these new results. So if you have some questions, feel free to interrupt, and if you don't hear me, please let me know. Okay, so first off, the motivation for this kind of works and explorations with modular symmetries is the flavor puzzle. And as you know, the flavor puzzle comes from observing masses and mixing of the known fermions in a linear scale or a logarithmic scale, as is here below. And you see that there is this kind of hierarchical structure that suggests some mechanism maybe behind these patterns. Okay, so there are huge gaps in the mass spectrum that we don't know how to account for. And also we have a very specific kind of mixing for quarks, which is close to the identity, whereas for the leptons, it's all over the place. So it's this matrix has large mixing, the PMNS matrix. One element at most is tiny, this 1,3 element here. And by now we're reaching a precision era in, for instance, neutrino physics, where the parameters in neutrino mixing, lepton mixing and oscillations are increasingly well measured. So here what you see is basically the point here is just to say that we have a huge precision in the angles, but the phase is still one of not very well known. So for a spectrum with normal ordering, the picture is this one. We have two large mixing angles, one small, and the phase delta, which is not so constrained yet as you would like. And in the future, we hope to determine, know more about it. Okay, so the question here about the flavor puzzle, if is there an organizing principle behind these patterns of masses and mixing? And one of the traditional answers to these questions is, suppose you take not a root of anarchy, but a root of symmetry, then maybe a flavor symmetry could be acting here. Flavor symmetry is essentially something that acts across generations, so unifies the generations horizontally in this image, as opposed to vertical or gut symmetries, which unify within the same generation leptons and quarks. And this is the approach of flavor symmetries. I'll not go into detail here, but we try to unify the generations in some kind of multiplets under the law of some symmetry group. And this will, in turn, determine their masses, their mixing patterns, and sometimes even the CP violation phases. So indeed, this is the usual approach of non-abelian discrete flavor symmetries, where you can either build your own models based on some flavor group, or you can try some model-independent approaches relying on saying which kind of residual symmetries may still exist, or how, some more general analysis. The point I want to make here is that this usual approach is good to constrain mixings, for instance, in the lepton sector and the Dirac CP violation phase. Usually it has some problems, which are here depicted as phis, meaning you have to break this symmetry. The symmetry is based on some group GF, and you have to break it to get something that matches data. And in the typical approach, you may have to break your nice symmetry in a very ugly manner with lots of flavon fields, which are controlled by potentials, which you have to drive to a good minimum. So in this case, you may perhaps need to invoke these Zn shaping symmetries. You can get quite difficult potentials with a very small number of fields. And then there is also this problem of the height, let's say what you are trying to do with your flavor symmetry. So the approach of modular symmetries is kind of a generalization of the flavor symmetries, the traditional ones, and it kind of comes into the rescue to, let's say, generalize this paradigm to get rid of some problems with the traditional flavor symmetries. This approach to the flavor was proposed by Ferruccio in this paper 1706, based on some results that were already known in the string community. And the point is that with these symmetries, you can get into a situation where you are so restricted that it's not just the mixing you constrain, it's the masses, and not just the Dirac phase, but also the Majorana. In a sense, you fully constrain in the minimal setups the full, let's say, lepton mass matrices. And here I have a footnote saying that SUSY is required. So indeed, for now, the setup is supersymmetric because we need this property of SUSY, which is the holomorphicity of the superpotential, to really say that our couplings are modular forms. We will see what this means, but to really get a predictive scenario. Okay. So this is also the cape. Why there is the cape in this superhero, it is supersymmetric, as well as a generalization of the usual paradigm. And let me tell you briefly that first we get rid of those 5 fields in the minimal. If we want, we can get rid of these flavons. So it's a flavon-free setup. You can get a flavon-free setup because your symmetry is broken in the minimal case only by the wave of one scalar field, which is this modulus, is tau. So it's a complex number living in the upper half plane, meaning that imaginary part is positive, and the wave of this modulus will do all the breaking of the symmetry for you. And the goal here with these modular symmetries is to get not just the neutrino masses mixing Dirac and Majorana phases, but we're really ambitious and would be wonderful if we could get naturally correct the fermion masses with their hierarchies, the observed mixing with its peculiarities, and all the CP-V phases somehow from this kind of scenarios. So this is a goal which is not yet achieved, but there are a lot of efforts in this direction. And this is the introduction of the motivation. Now I'll tell you how does the modular symmetry work. Okay? So where does it come from? Well, it can be coming from some torus compactification of extra dimensions. And this tau modulus that I told you about, this complex number, is a description of the torus. Now, I will be dealing with a bottom-up approach for most of the talk. So essentially, this tau breaks the symmetry, is like a spurion, and we don't care necessarily how it originates. But it's nice to know that there is this motivation from strings, where if you have 2 tori with different taus, described by different complex numbers tau and tau prime, they may actually be the same torus if these taus are related by a fractional linear transformation. So if tau prime is this function a tau plus b over c tau plus d, so this relation between the taus, you are essentially describing the same lattice, where a, b, c, and d are integers, and they verify this property ad minus bc is 1. If you are in these conditions, you are basically having the same lattice, the same torus for different values of tau. And this is the modular symmetry. Okay, so if you want this, the modular group is the group of these transformations which leave the lattice invariant. you can say it's the set of these matrices gamma A, B, C, D, with determinant 1 is just the condition here below, and with A, B, C, D integers, which act on tau like this. So they bring tau to A, tau plus B over C, tau plus D. And this is the modular group, which I'm calling capital gamma. So the set of all these matrices. This is not extremely relevant, but it's just so you have some notion of what this modular group is, the set of these transformations of tau, how it can be presented in terms of three generators. So there is a generator S, T, and R obeying these relations between themselves. This is a presentation of the group. But this is also not telling you much if you look at it. So let me rephrase. S is the generator which sends tau to minus 1 over tau. Okay, so the matrix A, B, C, D is 0, 1, minus 1, 0. T is the generator that brings tau to tau plus 1. It's a translation. And then if you want, you can have or not the R generator, which does nothing to tau, as you can check by putting A and C equal to minus 1, B and D equal to 0. Tau stays, A and D equal to minus 1, C and B equal to 0. And then tau stays tau. So it's a redundant generator, but can affect the fields. So you may wish to keep it or not. But essentially, the model group is this, the group of these fractional linear transformations that is generated by these S, T, and R elements. And I told you that tau is the only thing which breaks the model group. So it is like a spurion. When it gets a VEV, tau can no longer transform, and so the modular group is broken. Okay? And this is very interesting, on one hand, to play with tau, but of course we want to know how fields transform, because otherwise how do we do the usual physics of flavor symmetries? We need to know how fields transform and how tau has something to say about field transformation. So, okay, the modular group is this, transforming this tau number, fine, but now let's look at fields. How do fields transform under a modular transformation, gamma? So gamma is this, an element of the modular group, A, B, C, D, okay? And so a field transforms to C tau plus D, which is a number, to the minus K, which is some power, times representation, unitary representation rho, times the field. So if you forget this first factor, you get just the usual flavor symmetry rule. This is a new factor that appears when you are considering modular symmetry, but the rest is just rho. Psi is just the usual rule for transforming fields in a multiplets in a flavor symmetric theory. Now, the new factor, this automorphic factor, C tau plus D, has tau explicitly. So you now start to see that tau kind of mixes here with the fields in some way in these modular transformations. And there is a weight here is the exponent kappa or minus kappa, depending on how you define it. And while I will focus on kappa integer, I mean, this can actually be a rational number. There have been works from the top down, and then they find it rational. But the point is this kappa is either integer or rational for our purposes. And this rho is the usual unitary matrix. Now, unitary matrix representations of finite groups, fine, we know this. We take the finite group, we can find the unitary representation. But the model group is infinite. So the idea behind this by Ferruccio in this paper was to trivialize almost the whole modular group in this sense. There are these subgroups gamma of n. Okay, these are the so-called principal congruence subgroups of the whole modular group. You fix this capital N, let's say n is 4. And then this is the set of all elements of the modular group, which element-wise are the identity modulo 4. Okay. You don't need to care so much about the definition of this, The point is that also these subgroups are infinite. And if you do something like the representation rho of an element of this group goes to the identity, the representation of some element T times some element of this subgroup goes to rho of T and so on, you can factor out this infinite subgroup. Because every element, it's a normal subgroup, every element of the full modular every element of the full modular group can be written as some elements times an element from this gamma of n. So the point here is that you throw away an infinite part and you get essentially this quotient here, gamma prime n, which is the full modular group quotiented by this gamma of n. And this is a finite group. And then you know how to deal with finite groups. You get the unitary representations, and that's it. So in a sense, after this idea has been employed, you are in a situation which differs little from the usual one, except for this new automorphy factor. Okay, so you see that here, what we care about then is this finite group gamma prime of n. It's the group that matters in the end, even though we start with this huge modular group of all fractional linear transformations. And these finite groups gamma prime of n, they are well known, because if you see this table here, you find that when n is small, let's say 2, 3, 4, 5, you recover, these groups are isomorphic to very well-known groups in the flavor symmetry business. So if n is 2, this gamma prime of n is S3, the permutation of 3 elements. If we have n equals 3, gamma prime of n is T prime. It's a double cover of A4. In fact, the second row is what you get from the previous slide. If you just forget about the R generator, the groups you get are even simpler. Basically, the finite modular groups are S3, A4, S4, A5, and their double covers, let's say. So you end up working in something very similar to what was known with the traditional modular symmetries, but with some extra twist of predictivity due to holomorphicity, which I'll get to in a minute. Just to say that a lot of works have been done for each of these groups and extensions. So you see here some references that I'm flashing, but the references now are over 150, so it's impossible to keep track of all them. These are just the ones where these groups were first mentioned. And here in green, I have a paper of ours which has an appendix summarizing these 4 major groups. Now, here comes the new part. So if the fields transform, as we saw, this is the second line here, what happens? So what? You have your theory described by a superpotential, W, and this is a collection of all the singlets you can make with some constants, G. So you have to make singlets out of the fields, but now it's not just a matter of canceling the rows, because there is also this new factor C tau plus D to some exponent. This means that when your fields transform and you want to say your superpotential is invariant or changes by some constant term, okay, for our purposes, let's say it's invariant, then you have to cancel not just the representation matrices rho, like in the usual flavor symmetry, but also all these C tau plus D factors. So these factors depend on tau. So what actually happens is that you have to form the singlet, you have to have some function of tau, which transforms in a way that counteracts the transformations of the fields. And these functions are very constrained and very well known to mathematicians. They are modular forms. Okay, so as long as here your exponents add up to cancel the exponent of this function of tau, y of tau, and this representation matrix rho of y can, with the other representations, make a singlet, you get your invariant. Okay, so essentially, this is what you need. You need functions which transform in this way when you apply a modular transformation. And so actually, remember, these y of tau are just functions of tau. You know how tau transforms under a modular transformation. It goes to a tau plus b over c tau plus d. So modular forms are the functions which satisfy this relation here in the blue box. And why are these guys important? There are not so many of them. This is why the setup is predictive. So you want to build singlets, you try to build your singlets, but you find that the number of modular forms is restricted. There is a finite set once you set the weights, these exponents for the fields, which I am calling weights, and you chose your group. Basically, the number of modular forms that you have available is small. So for instance, here, let's see if your group is gamma 3, which is A4 here on the right-hand side, there is just one modular form available. It's this Y3 of 2, weight 2. If you increase this weight, you have more, but at lowest weight, you just have this triplets of A4, and that's it. So it's not that you can build anything in your superpotential and constricted Lagrangian in the end. So to make this all more concrete, less abstract, let me make you an example before we move on. Let's build together a modular-invariant term. By the way, I'm noticing that my connection may be unstable, so please let me know if you stop hearing me for some extended period of time. All right, so how do we build a modular-invariant term? Let's say we want to have right-handed neutrinos in your theory, and we want a Marana term for them. So in their superpotential, there will be a term which is basically n squared, where n is the superfield associated to these right-handed neutrinos. Now we choose a group and we choose a representation for the n field. Can you hear me, by the way?
Yes, I can hear you.
Okay, sorry. I got a message from Zoom and I was afraid I got disconnected. So here in this example, let's say this n, which is the right-handed neutrino field, is a triplet and has weight 1 under the modular group, which is A4 modular group. So the quotient of the modular group by gamma of 3. And we drop the R generator. Essentially, what you have now is that your superpotential is not invariant if your n transforms, because you would get some factor c tau plus d. So you need to build in the singlets in your invariant superpotential, including the function that I just discussed before. So the only triplet available at the weight necessary to cancel the exponent coming from this n and from this n, right? Because there's c tau plus d to the -1 from both ends. So this -2 exponent will have to be cancelled by a +2 exponent. This is provided by this function of tau. And then you check what this y32 is. It's a well-known function of tau. And then you find the invariant via Clebsch-Gordon's. So you build this mass matrix. It's the only invariant that you can have. And you can count the number of parameters. And you see that aside from an overall scale, which is a free parameter, you have only another free parameter, which is tau. As soon as tau gets a VEV, which is just fixing this complex number, your matrix is fixed. So you have the mass matrix of the right-handed neutrinos that will be used in your diagonalization has this form. And here, with this simple example, you can see the the promising constraining power of modular symmetries. Of course, we are not satisfied doing just this for the right-handed neutrino mass matrix. So let me show you a real example, let's say a full lepton model. This is a model from this paper where we consider the modular S4 finite group. Of course, we have to choose the field contact, and this means choosing the representations and the weights of the right-handed neutrinos, the lepton doublets, and the charged lepton superfield. So this is basically the choice of representations and weights, and the superpotential we built is this one. So you see that every term we put, aside from actually in this example, the Majorana term doesn't need any modular forms because the weight is 0, and you can just fill the singlet directly. But all the other terms have a function of tau. So you have to, in the bottom-up approach, you just fit. You try to minimize the chi-square by varying the tau and your other parameters, alpha, beta, gamma, and let's say the important things are g square over lambda and the ratio g prime over g. So we fit the couplings when tau, and in this case, we did find a fit. Let me just briefly mention that this g prime is in general constant. It's in general complex. All the other phases can be absorbed, but the g prime has a phase which is physical. If you combine your modular symmetry with the generalized CP symmetry, you can make this g prime real. This is another work we did with also with Arseniy Titov. It's this 1905 paper down here, and we've shown that tau could be the only source of CP violation. So you can actually make all your parameters real and reduce 1 degree of freedom in your fit. And we found indeed that a fit of the lepton sector was possible with several predictions. So in this example, our prediction for the octant of θ23 is the lowest one. The sine square is 0.49. We found the prediction for delta and the Majorana phases, leading to a prediction for the neutrinoless double beta decay Majorana effective mass. And as I told you, we can constrain the masses of the neutrinos themselves. So in this case, we found that the sum of neutrino masses was 0.08 electron volts, with some correlations between the observables. So if you increase precision, you could in principle rule out this model. And we did this by using 7 parameters, 3 of which were the charged lepton masses. So in the end, 4 for the neutrino sector to get 9 observables, which some of them are not yet measured. Okay, so in short, with this part of the presentation, I tried to convince you that modular symmetry is constraining. It's strong to constrain your theory. Basically, there is a scale factor in the field transformation aside from the usual unitary rotation, and your superpotential, your invariants turn out to be functions of the superpotential parameters and a single complex parameter tau in the minimal case. Okay. So before I carry on, let me just tell you a bit of a personal view of where we should be going or can go from here. I mean, the community is actively trying to use the modular symmetries to explain the mass hierarchies, and this is something I'll discuss in what follows. But it would be also interesting to find a clear connection between the mixing patterns we fit and the structures the modular symmetry is predicting. So not just fits numerically, but really understand the connections. This is not, I don't think this is yet clear. I mean, people either put texture zeros because they want texture zeros, or they fit without caring what is really happening. I mean, if you fit, you fit. If you don't, okay, this is a kind of personal view. Now, from the top down, TV is top down, we could try to find some way to fix the freedom in this setup, because you may notice, you have a lot of freedom. You can choose the weights of your fields. You can choose the representations under the finite groups. So it would be nice to also have some hints to fix these quantities and these choices. It would be nice to have some universal predictions of these scenarios. And actually, there was a couple of papers by Ferulho on this possible universality near some symmetric points, which will also be discussed in what follows. Of course, phenomenology beyond masses mixing is welcome, not just fitting and predicting masses or missing or CP violation, but something more. And to do away with SUSY also be interesting. So let me not take a long time here, and just now we have the background, let's say, to discuss how fermion mass hierarchies can arise from modular symmetries, and not just put by hand, because there has been a lot of work on mixing, okay, particularly lepton mixing. But the mass hierarchies before this paper were usually put in by hand. So you have the superpotential parameters aside from tau, and in this model that I've shown you, we get the fit by putting in very hierarchical superpotential parameters. So in this model here, this gamma, alpha, and beta were just fitted, and the fit gives you hierarchical constants, and you say, I don't care. But you can say that you do care. And so, for instance, these authors here have tried some approach where you add a scalar, which has a weight factor as well, so non-trivial weight. And this scalar can play the role of Frogat-Nielsen fields, where the weights play a role of the Frogat-Nielsen charges. So you can kind of justify the fermion mass hierarchies, not by fine-tuned constants, but by a new field. What we try to do is different, in the sense that we don't add new scalars. We just use tau, which is the field that we have there already. We can do this using common weights across the generations, so it doesn't need to work with like Frogat-Nielsen at all. And this is the approach I will summarize in the next few slides. So it's an idea to get mass hierarchies of fermions, which by now has been applied in several works here. But the key point is this, is that we are preserving or almost preserving a residual modular symmetry. So we have the full modular symmetry, large group, and I told you that tau breaks this group because as soon as it gets a VEV, you can no longer transform tau, modular symmetry is broken. Okay, but by the way, let me just tell you as a side note, you can restrict tau to this blue region called the fundamental domain. And essentially, it's the same as any tau you could choose. I mean, you can map models to this fundamental domain. So you can restrict tau values to be inside this blue area. But the point is, any value of tau breaks the modular symmetry, except that at specific values of tau, you don't break completely the modular symmetry. You still retain some residual symmetry. So if tau or equivalent values of tau correspond to this tau equal I, this middle point here, you break the modular group, but not a Z2 symmetry associated to the S generator. Okay, similarly, you are almost preserving this Zn symmetry. N is the order of the finite modular group. And you are essentially not breaking the T generator. And finally, when tau is at this value omega, so the cube root of the identity, which is also called the cusp, okay, you preserve a Z3 symmetry. And when you preserve the Z3 symmetry, you are preserving the product of the S and T generators. Okay, so you preserve the product ST. This element is unbroken. And you can notice or already try to guess that, oh, if we keep some symmetry alive, if we keep some residual symmetry, then you have constraints in your mass matrices. And in particular, some couplings, this is the key idea, some couplings will vanish when you are at a symmetric point, or be very small if you are close to a symmetric point. So for instance, let's say you are sitting at one of these three symmetric points, either I infinity, which is large imaginary part of tau, or the cusp omega. Your mass matrix could look something like this. Okay, so this is M, is the mass matrix. And if the idea is if you deviate slightly from the symmetric points, so if there is some epsilon deviation from this point, these zeros are no longer strict zeros, but your mass matrix is populated, all these zero entries are populated by powers of this epsilon. In fact, you can show, and this is, we demonstrated that in the vicinity of the symmetric point, all zeros are lifted to powers of this epsilon, and the powers depend just on the residual, on a field decomposition under the residual group. Those forms, you can check some tables, you see what kind of power you expect here for a value of tau, which is close but not quite at a symmetric point. And we did this analysis in generality for, well, for the small modular groups and up to and including 5. So as I told you, at I, the residual symmetry is Z2, omega, this cusp is Z3, I infinity is Zn. And what we found is that the possible powers of epsilon filling these entries, zero entries of the matrix, were in correspondence with the group. So if your group is at 2, basically these powers, either you get order 1 breaking of the symmetry or order epsilon. If you are close to omega, your breaking could be order 1, order epsilon, or order epsilon squared. And you can get higher powers of epsilon at I infinity. So the first case was explored for a specific group a little before us, and it leads to a massless fermion. So in this work, we focused on the other 2 cases, which allow for a fully hierarchical spectrum, in the sense that at first order, you just have one massive fermion. Then you are taking into account this small deviation from the symmetric point, and you can get hierarchies like 1 epsilon epsilon squared, or 1 epsilon epsilon cubed. So essentially, you can get no massless fermions and all of them hierarchical. As I told you, I mean, I'm not going into the details, but it depends which powers and which exponents L depend on how the fields decompose. This is the bit of group theory, but we determined everything for n up to 5. Let me give you an example. For instance, if you are working with n equal to 5, you are working with modular A5, and suppose you have 2 fields, psi and psi c. There are 2 triplet representations of A5. Now, in this analysis, you do the bit of group theory. You, let's say, the imaginary part of tau is large, so you are close to I infinity in some sense, and you find how your groups decompose at this symmetric. Sorry, how your fields decompose at this symmetric point. And with this bit of group theory, you can find the powers that populate the zero entries in your mass matrix. So this epsilon is a small parameter. In this example, is kind of suppressed by large power of imaginary of tau. And you get this kind of matrix, which leads to this kind of fermion spectrum. So you can get a hierarchical spectrum of fermions where the hierarchy is controlled by the closeness of this tau to the symmetric point. Okay? And let me stress that this is very powerful, more powerful than Frogat-Nielsen in principle, because while here you have this tilde and, oh, okay, every entry is, let's say, some power of epsilon, but there are order 1 coefficients there, like Frogat-Nielsen? The answer is no. There are no order 1 coefficients. In fact, group theory determines exactly the coefficients of each of these terms. So it's not like Frogat-Nielsen, it's kind of an improvement, because what you get is that your mass matrix is a very well-defined function of tau. There are no, dependent on these functions of tau, there are no order 1 parameter for each entry necessarily. In fact, for this very minimal example, you could get even just one constant, aside from fixing the value of tau. So while this example here does not work phenomenologically, it is just here to show you that this is predictive. You are not left with this order one ambiguity in each entry if you want. Okay, so you can get hierarchies. In fact, this is just a sample of our table. We identified basically all the representations, all the weights for all the three symmetric points, which could lead to viable fermion hierarchies. So when you break the symmetry, basically close to a residual symmetry point, you get something which has fermions which are hierarchical. Okay, and here this point, this one that is marked in gold, is the one corresponding to the previous example. Okay, there are some cases which we don't care much about because they introduce too many parameters if you go and build a model. So here, for instance, in these ones that are in red, they're fine in the sense of hierarchies, but they are, if you build a model, you have too many superpotential parameters because you have, let's say, there are 3 copies of a singlet. It turns out that if you try to build a model, you get too many parameters. So what we did is we found all these possible spectra, and then we just kept a promising spectrum. Okay, so we found that for these 4 groups, which are the double covers but include the original ones, the promising is 1 epsilon epsilon squared, or could be even epsilon cube or epsilon 4 in some special cases. Okay, so let me just tell you that very briefly, flash that only some pairs of representations lead to these patterns. So we encoded them here, but this is not to read in 10 seconds. Basically, only some pairs of representations work and lead to these patterns. Okay, so we tried some of them, and we found that the ones which only had triplets or triplets and at most 1 singlet. Here are the 2 cases we explored in some depth, and we found that indeed, and we could fit everything actually in the left-hand sector in these 2 models. So we chose in the end these representations. We verified that we get this pattern of masses, and we were very happy. But we went to look closer, and despite the fact that you can fit, we find that there is a fine-tuning. So we would get the correct PMNS, but then we would try to change a bit the parameters, and everything would be mixed and not matching the data. So what was happening is that we were not getting a good enough PMNS in the symmetric limits. So we were relying on cancellations, fine-tuning to get the fits. Okay, so it means we need to apply a second filter to this table of promising cases, which would be a filter of natural mixing. So not just mass hierarchies, but mixing. Let's avoid fine-tuning in the mixing, and here we focused on the left-hand sector again. So what could be a PMNS which is viable in the symmetric limits? Well, there is only, let's say, 1 small parameter in the PMNS. It's symmetry. There is a 0 in the top right entry. Fine, because we can lift it basically with epsilon and still get something which looks like the PMNS. Or maybe we all have all entries populated. We just don't care about cases where you have zeros elsewhere. And the conditions for finding such, let's say, good PMNS or quasi-PMNS in the symmetric limit, they were studied before in this paper here. I will not go into the details. The point is that you need to have some further condition on the representations of the fields, and then you use this as a filter, and basically a lot of your cases go away. So when you imply this condition to the table that was here, this full table, you are left only with these cases. And naturally, we wanted to explore the most predictive of these cases, which still has 9 parameters. It's this one. It has a triplet of S4, and the doublets are transforming as these singlets 1, 1, 1 prime of S4. This will lead to a pattern of masses, which is 1 epsilon epsilon square, if your tau is close to the cusp, this omega, which is the cube root of identity. Okay, so we performed this fit, and we found several models. This is, let's say, the minimal model, which I didn't sigma range, but there were several models which would work with these kind of assignments. Of course, we build a superpotential as before. We impose GCP. This means that all these constants are real, and the value of tau is the only source of CP symmetry breaking. So what we get is from this superpotential these mass matrices in an appropriate basis. And this epsilon, when you are close to tau, you can basically write it as this proportional to this difference tau minus omega, which is your deviation. Now, I'm just writing it here like in this expression to point out something, because this parameter u is also another way of quantifying the deviation of tau from these symmetric points, the cusp, and it will be useful in the last part of this talk. Okay, but essentially there is a small parameter epsilon. It's 0 when you are at the cusp, it's small when you are close, and fits with epsilon of the order of 0.02. At the same time, no big fine-tuning in this following senses. These constants A, B, alpha, beta, gamma, they are not hierarchical, they are order 1. Another sense in which they are not fine-tuned is that you see they have rather large error bars, in the sense that if you vary them a bit, you will not spoil the agreement. So even though you have here 1, 2, 3, 4, 5 meters plus tau, okay, you are getting some predictions. So this is a lepton model close to omega, where I'm zooming in here in omega. This is a zoom in the fundamental domain. So you see tau is constrained to be in a ring around this point. And this epsilon, or u are small, you get the masses, as I told you, 1 epsilon epsilon squared. The coefficients are determined by group theory and the superpotential constants, which are not hierarchical, and ordering like the symmetry mass is 0, and delta is very, very close to pi. So leptonic CP violation is small, with the prediction also of this m beta beta around 1.4. So this is a model which naturally allows for hierarchies as we wanted, large mixing, natural large mixing, and some predictivity. So now I can summarize this part, that fermion mass hierarchies can arise, not just from tuning things, but if tau is in some special place, like close to a point of residual symmetry. You don't need flavons for this. You can get, for instance, natural lepton mixing. And it turns out that if you say also you don't want fine-tune mixing, you have a very restricted setup. You cannot choose any representation you want, just some work. Now, since I have a little time left, I will just present the flavor of the other paper, which is answering this question here. We needed to fit, for this model, we needed 2, or equivalently this U.007. And of course, you may wonder, okay, you trade one fine-tuning for another. So we are not happy, of course. What I want to tell you is that it's not necessarily the case, and there may be a dynamical reason for this small value of deviation. So for tau, taking a VEV close to a symmetric point. And this is the part of modulus stabilisation, where we basically revisited some results from the 90s, okay, where we looked at simple modular invariant potentials coming from supergravity. So here we were very agnostic to the origins of this potential. We just took basically the same Kähler and superpotential as in this paper, and we focused on the case of modular weight of the superpotential -3. It's a simplified model, so it doesn't matter which finite modular invariant, and see what they tell us where these guys have minima. So what would be the values of tau? This is simplified. There have been some advances also to add matter, but here we'll focus just on functions of tau. And the potential V can be extracted from the superpotential W and from the Kähler K. Okay, so I will not worry with details. This V is given. These are some relations between the constants, but essentially the only thing here that is left to fix is this H function of tau, and we fix n equals 3 as in the previous slide. So basically your potential V is a potential for tau, which is fixed as soon as you specify H, and it's a modular invariant potential for tau. Okay, so this H should be the most general holomorphic function to parameterize it, which they claim to be the most general. And the simplest way is by basically using this J function. This is a function of tau, called also the Klein invariant. And there is a potential which we can fix to 1 as a simple choice. If you do that, you can maybe motivate it. We have some reasoning to motivate this, but in the end, all your potential depends on, which is modular invariant, is CP invariant. You can put it into the program of your choice because you can write it in terms of the Dedekind data function, which is well known. And in fact, let me just tell you that this is the eta function, has a very well-known cusp. So in terms of this U parameter, and it's a very well-controlled expansion. We basically expand this potential here for different values of M and N, okay? And we find the global minima. Now, the authors of this paper already had found global minima for some values of M and N. For instance, when M and N are 0, everything is fixed. The potential looks like this, and to I. Okay, so it's something which is far away from the cusp. It's does not break CP. We also verify the results. We verify the results for M and N equal to 1, for M equal to 0 and N equal to 3. We find the minima at the same places they found. However, what we do find is that against the conjecture they had, it's not true that all minima lie on the boundary of the fundamental domain. If you zoom in on this left plot, you will see the right plot. You will see that there are global minima of modular invariant potentials, which are not on a symmetric point or on the boundary. These values are breaking the modular symmetry, close to the symmetric point, but not quite at the symmetric point. And they break also the CP symmetry. Okay, so these are new minima, they were not found, and it goes against their conjecture. These results were also recently confirmed by a paper from December. So what we found are these minima, the ones they find, the one at the symmetric point tau equal y, that one is exactly at I, some around the arc, but no minimum at the cusp, just close. And in fact, we were very careful to expand the potential to find how close. So I will not bore you again with the details. So shape, and you find that basically these minima only depend on one integer. It's m. N is set to 0, and you have a series of minima which are close to the cusp but not at the cusp. So also we check the phase dependence to check really if we are not on the boundary as they conjectured. We found that the phase is around -40 degrees. This means essentially that our minima are here in the left plot in the intersection between the dashed line and this deeper curve. So not at omega close, and for m bigger, let's say m equal if you compute the deviation, you get very close. I mean, you get basically the same that you needed in the model. So we were quite surprised by this. In fact, this is kind of a matching of the puzzle pieces in the flavor puzzle. We find that the value for one of the values of this global minima is completely what you need for your fit explaining the hierarchies. We were surprised. Of course, this is a simplified model, but we were already surprised making these models more realistic by adding matter, because these minima were anti-de Sitter. In the end, they still find the minima close to the cusp, so it's not that we ruin this prediction. And now I'm seeing that I am basically out of time, so let me just summarize that in this second paper, we looked at simple potentials for the model stabilization, finding new CP breaking minima, which are not at the cusp, but in its vicinity, matching the sizes that we wanted for the phenomenology. So thank you very much for your time and attention. Please let me know if you have some questions.
Thank you very much, Joao, for the very nice and complete talk. Question from the audience? There's some question from the audience. Joao, you were showing before some potential for this stabilization. How this potential are derived? One of these potential was connected with this the was inspiring supersymmetry and Sugra.
Yes. So these potentials were built from this scalar, which is just a function of tau, and this superpotential here, which is basically this H function is all you need to specify, and it's something that has weight 0. Once you specify this K and W, you get the potential from this expression. This is the Sugra expression.
So it's some sort of
just putting in this V. Sorry?
It's some sort of Kähler potential. It looks like a Kähler potential.
No, yeah, it's this one.
Yes, indeed.
I think the authors, they work it out from Gaugino condensation, but I'm not an expert at all. So what we did is just follow their choices, and what we find is for this simple case n equals 3, which is actually motivated by the number of dimensions you need to completify. You need to completify 3 complex dimensions, and you find the potential given as a function of h, which in the simple case is also just a function of 2 integers, right? So let's say you fix n to 0 and m to 1, you find just one global minima, one pair of global minima. Sorry, let me show it here. So if m is 1 and n is 0, you find this 1, 0 dot versus to the cusp and other side of the fundamental domain. These are degenerates. And the authors of this paper in the 90s also did this analysis for the potentials, but they somehow missed this class of minima, which are not exactly on the cusp.
Yeah, and between this modular model, this modular S4 flavor model and modular A5 flavor model, which, in your opinion, you think is more gives more consistency with experimental data with less parameter? Because you were mentioning modular S, you briefly mentioned modular A5 and also modular S4. Which of this model
Yes.
is best? Is better?
If I recall correctly, if you are just going by less number of parameters, I think there is a model by Ding, which is either A4 or S4. Now I don't remember, but it's reliant on fine-tuning. Maybe it's S4. Usually, when you can get something with A4, you can sometimes get it also with S4, but most of the cases. And I don't know the answer of an open question. How predictive you can make your model from the bottom up when you just have this requirement that nothing is fine-tuned. So if you look here, we still have a lot of parameters. I mean, not
So maybe A5 model will be less predicted because the tensor product got richer, and one could have also quintuplets.
And in the quark sector is even worse. Sorry?
Maybe A5 model will be less predictive.
A5 model, there is a chance to be very predictive, but not for leptons in three-dimensional representation. So if you have something bigger, maybe, because A5 has nice properties. You see here, there is only one pair of representations for A5, which gives you the hierarchical pattern.
And why there are the other possibilities do not work?
In mind, this analysis was restricted to, sure, let me tell you. So first of all, we had an assumption, which is common weights across generations. If you lift this assumption, I guess you can get more cases than the ones you have here. But why the other cases don't work, you can find the analysis. Here is the table, and you try to see what kind of patterns you get. It turns out that either your spectrum is like a degenerate spectrum, or it's this one where it's 3 with 3 prime, or it's a triplet and 3 singlets. A5 only has 1 singlet, right? So what you can do is this. Maybe you can ask, but A5 prime, the double cover, has doublets. Well, but if you include doublets and the singlets, there is a selection rule, they don't mix, and you get problems with the mixing, both for quarks and for leptons. This is general. So in the end, what you find is these models in the boxes are the promising ones, but then you throw away the ones in red because you have 3 copies of the same representation. And if you really want no massless fermion, you have to have enough linear combinations of the modular forms, high enough weights to not get rows of your mass matrix which are proportional. Right? You see that if I give, let's say, the same weight to all these 3 fields, you get basically the same rows in the mass matrix, and the determinant is 0.
See, yes, will not be viable. They should have the same weight.
Yes, so different weight. And even if they have different weights, the modular forms are so restricted and so connected that usually even then the rows are proportional. So you have to be careful. You have to have, I think, at least 6 superpotential constants in these models. And it's already too much. This is not, so this is the hierarchies of the charged leptons, right? And this is a lot because you also then have the neutrino sector and you quickly reach more than 10 parameters. I don't know if I answered your question.
Yes, you are. Thank you, Joao.
Well, thank you.
More
Thank you
questions
for
from the
having me.
audience? Any more questions? And I had the last question, Joao. In your model, how you consider also the possibility of having Kobe-maximal texture in the
Sure.
neutrino sector?
So in my model, what you mean texture in the neutrino sector? You mean this?
Kobe-maximal texture? Kobe-maximal missing? Have you considered the possibility of having?
So I can tell there's a paper by Novichkov, which is one of the authors of these papers, Petkov, the other author, and Tanimoto, which discusses trimaximal. And I think a generalization maybe bimaximal, but then you need to do some careful choices. And so I don't know how to answer your question, but I for sure it can be done using the residual symmetries. I don't know how compatible it would be with mass hierarchies.
See, because maybe it will be different. Yes, there will be the part of the lepton sector that maybe with some appropriate choice for the triplet. If you use A4 or S4, it can be make it diagonal to have the neutrino texture, to have Kobe-maximal structures that will require some bed direction. Maybe along some direction of the groups.
Right, maybe you need to add a flavon, which on one hand maybe be less minimal, but on the other can help you with quirks. So I will not say this with certainty, but you can, because the literature is already very vast, but I'm not sure if anyone has a model dedicated to Kobe-maximal. I would have to search.
Just also check that part, because it's a nice missing pattern.
Yes, it's nice if you can get something else also out of it. If you, let's say, see that you have to add flavons or another modulus, then maybe you can use this extra structure to fit quarks at the same time. Because there have been a lot of works working on both leptons and quarks, so on the unification.
More questions from the audience? If there are no more questions, we send the speaker again, and we meet at the next seminar. Thank you very much, Joao.
Thank you very much for having me up here.
Thank you very much.
And
goodbye.
Hope to see you soon in Lisbon.
I see you soon in Lisbon. I see you. Bye. Ciao.